All right, good morning. Let's start. Do you have any questions? Okay, so let's begin with housekeeping. So for the midterm, right, your first midterm,
Oh, I'm sorry. Is it just me or everybody else cannot see the screen?
it's not you. I forgot to share. I apologize. Thank you for letting me know. Uh, let's see. Try again. Okay, good, right? So midterm one next Friday. I talked about the one page of notes, one-sided, right? You will submit the notes with the exam. Material will be capped by today, meaning everything from beginning up to 10.3 minus Chimera lower bound. Okay, so 10.3 has two topics: efficiency, which is a concept, and then Chimera lower bound, which is a theorem that you won't be responsible for midterm one. So 10.3 means it still includes 10.7, 10.8, all right? Because I mean, time-wise, not like chapter-wise, okay? So everything we cover up to 10.3, which is today's material. Yeah, so you're expected to be familiar with, right, homework, quiz, results, lecture results, that kind of thing. If we have done something, right, in class, for example, you can quote any identity, right, quote any result without proof, For example, expectation of s squared equals to sigma square, the sum of xi minus mu square is sum of xi minus x bar square plus n x bar minus mu square. I mean, if it's appropriate, right? I don't know. But if you want to quote them, go ahead and quote them without any explanation, any proof, all right? The point is to solve the problem, not to re-explain what we have done, all right? Of course, I mean, if it's correct and it's appropriate for the situation, if you quote the wrong thing for the wrong problem, then you don't earn any credit anyway. Try not to leave anything blank, right? I give partial credit. The TA should too. The way I operate is I grade half, the TA grades half, all right? Can't speak for the TA grading. I usually let my TA decide their own grading criterion as long as it's consistent. But for myself, I give partial credit. But of course, right, blank question has no credit. So try not to leave it blank. In terms of, right, so yeah, right, familiar with homework and quizzes and stuff. Now, like I said before, I'm not gonna guarantee that my questions will repeat anything I have asked before, anything like that. But right, I mean, familiarity with homework and quizzes and my past exam might help in the sense that you see the style of the questions I like to ask. What else? Yes. In terms of like how you will conduct the exam, we will use lockdown browser. With camera on. So the session will be recorded, okay? So I can review if I have any question, I have anything issue. So with lockdown browser, right? You cannot open another browser. So what happens is the submission issue. So there will be two instances of midterm, midterm 1, hosted on Canvas by the class time. All right, it will be available. I'll post it the night before, but it will be available at 10:20 of the day of Friday. Okay, so one is one with lockdown browser, one without. Okay, and the one without will be for submission. Okay. You will have to do the exam with the one, right, with lockdown browser, right? Okay, do exam with this one because I will need to see the evidence, all right, that you do your exam under the monitoring of the lockdown browser. But after you're done, you can just turn off your, lockdown browser, and you will use this to submit, right, your exam. You will scan your exam. You will write down whatever. Okay. So of course there will be like a time interval where you are not monitored. So I would say, right, 5 to 10 minutes here. Okay. By the timestamp that I see on the submission, that you will have time to submit. Okay, so let me see here. I can't see the chat. Hold on. Oh yeah, Christine. Yes, you will be submitting a PDF. All right, you use like a one file, all right, PDF, scan whatever app that we use. So actually, I will give you 15 extra minutes, okay? Or 10 extra minutes, I don't know. 10, 15 extra minutes. So actually you will have so the exam will start 5 minutes before class. So I would say start at 10:15 and it will end at what is it? We end at 11:40, right? So it will end at 11:45. Okay. So that will account for, will we have class that day? So no, we won't have class that day. The homework will we do in the same day. Yes, the homework will we do on the same day. Homework this week, but at the end of the day, yeah. For Derek, if you don't email me the link, just email me the PDF file. Okay, but again, like issue, I would expect, yeah, go ahead and send me the PDF file anyway, but I will need to review, with the lockdown browser and things like that to kind of review what the issue is. So let me tell you that if like there's certain things that I cannot verify, okay, then I will ask you to have a kind of a live exam session with me where I ask you to do questions, okay, extra questions to decide on your grade for the midterm. So like an oral exam kind of thing. That's if I cannot, right, verify like that you did the exam in the proper way, whatever. So that's the last resort, that you will have to do an oral exam component with me. Can I send the lockdown browser download link? It's on Canvas, as far as I know. It's just a I don't know. There's no download link, whatever, right? Is there such a thing? I'm not sure what you're asking. What do you mean the latest one? Anything can be written on there. The restriction is that you cannot write a whole Bible on it. So I said before, right, that it's one-sided, 11 size font, single page, that kind of thing. You can handwrite it. It's just that, you know, make it reasonable like this, right? If you write like this, I have no issue. But if you write like, you know, a 5-point font, then you will, you know, be in problem with me, if you understand what I mean. All right. Yeah. So I understand that the monitoring uh, software may cause issue. That's why there is that okay, oral exam component. Now, again, like if you have to do the oral exam component with me, then of course, right, it'll be a live session and you'll answer questions live, okay? Where questions I will pick for myself. So there's always that, but I don't want to go that route because I prefer to compare students with the whole class rather than by themselves. Okay, I think that's that. Any other question? I will post, right, the whole guideline on the announcement again, but this is just a kind of the breakdown of that. All right. So no question. Yeah, you can send me an email because yeah, lockdown browser is really stupid. I mean, you can't really. Usually, I would be on, you know, Zoom, for example, for when students have questions, but lockdown browser just prevent you from doing that. So yes, if you can, you know, again, right, there'll be timestamp. You jump out quickly, whatever, send an email and jump back in. I think that's fine. Okay. So what else? What else? So the second thing is going to be quiz of this week. So I share with you my last two midterms from course this course I taught before. So I will pick problems. I think I'll pick two problems from the previous midterms. Just you know, so you know, if you don't practice it, you will have to be forced to do it anyway. So here's the option, because I guess you may want to see the solution for that before your exam. So you have two options. One, it will be due on Tuesday, okay, by end of day for this week only. If that's the case, then I'll post solutions to everything Wednesday morning, so you can study them. Be due Friday by end of day as usual. Then I will post solution to the midterms minus the quiz content. Okay, on Wednesday. Which one do you want? One? I'll go by democracy. So I see 3 votes for one vote for two. Anyone else? If you don't vote, I'll take it as neutral. You don't care. Okay, 2 for yeah, sorry, we're doing it really 50-50 now. I think, right? 50-50. Any tiebreaker? I'll cast a tiebreaker if there's only 50-50. Your imaginary friend. Christine, for some reason, you keep posting the same message. You like one, but you rather it be due on Wednesday. For you will have class on that day. We have class on Tuesday, right? You mean a different class? So you want it to be due on Wednesday instead? That's the change for option 1. Then I'll post, because I cannot post solution before the due time, right? So I'll post solution on Thursday. Yeah, I know. I mean, but you understand, right? Because the quiz, I can only post the quiz content solution after you turn it in. So that's why, right? I will post solution minus the quiz content anyway, but okay, so I think no more vote. Seems like last chance, no vote. I'll cast the tiebreaker then. Okay. All right. I think I'll go with 1 anyway. I like 1 for some reason. So okay, so option 1. Quiz this week will be due by Tuesday, end of day. All right. Cool. Oh, and by the way, right, when you study for the past midterm, do not get that as a guideline for the midterm of this semester. All right, like that's for your reference only. Also, when I taught the class the previous times, there are certain contents that I do not teach you this time, or I do not mention this time. For example, the Chevy-Chef inequalities, that kind of thing. All right. If I don't teach you, it won't be on the exam. Okay. So, but that's why the past exams are only for your reference. It doesn't mean anything about what I'll test this time. Okay. So let's begin the lecture then. Where were we, right? So last time we were in the middle of 10.2 and 10.3, where we discussed the idea of bias and efficiency. So the idea is that we have a estimator. Okay. So with 10.7, 10.8, and generally, right, given a IID sample that comes from a population that depends on with population parameter theta, then you can construct a statistic right? Theta hat being a statistic that depends on the axis, right? That's going to be your random statistic. That is an estimator for theta. Okay. How good is this estimator? How good is theta hat? Is the question, right? And so we mentioned that one of the very traditional evaluation of theta hat is through the so-called mean square error, MSE, which is the average error the average square error you commit, okay, when you make the estimation theta hat. And that will be, if you, this is expectation of the square, right? That will be the variance plus the expectation square. Okay, so pay attention. The difference, right? I hope you know, this is expectation of x squared. This is expectation square of x, meaning that this you square first before you take expectation, right? This you take expectation first before you square. So the variance, right, is related to what we call efficiency. And the expectation, right, is related to what we call bias or bias square. Okay. So that prompts us to define, right? Or actually, it's just like a classical concept that theta hat is unbiased for theta if it has no bias, right? So basically, you see this quantity without a square, right, represents the bias, meaning on average how much error you make, either above or below, right? So if expectation of theta hat equals to theta, then you have no bias. So that's why you're unbiased, right? It's biased otherwise. So for example, x bar, right? X bar is unbiased for mu, and s square is unbiased for sigma square. Okay. And again, right, you know, these statements are just rewriting what we wrote before, what meaning expectation of x bar is mu, expectation of s square equals to sigma square, right, under the assumption that x1 up to xn IID normal mu sigma square. Sorry, not even normal, right? You don't need normal, just mean mu variance sigma square. So actually here may be a good place for us to point out, right? And I got more than one question about this, so I want to address. I think these are good questions. I mean, the students listen to what I said and ask, mu being unknown, right? Because I say these are unknown population parameters, and I emphasize that. Does this statement make sense? Okay. Does it make sense that we say something like this because it's unknown? Or, right, when you think about it, does it make sense when we talk about the MSE? Because, right, theta is the unknown parameter, right? Abstractly, theta hat is the statistic we construct from the sample. You mean here? You're asking here or here? Sorry, I say yes too fast. Here, right? Yeah, it's a good observation, but you tell me. Should it be? It is, but right, for C constants. Is it okay? Yeah, correct. Yeah, good observation. But you know, it's awkward to write that because you know the idea is we want to consider in theta hat. But you're right, right? We keep this here because it matters. Here doesn't. Yeah. Okay, so back to what we were discussing, right? Theta we don't know. So does it make sense to talk about MSE? Well, the answer is right. That is exactly the spirit of this class. This statement makes sense. Okay. So let me just take a detour and say these statements make sense, right? Even if are unknown. Okay. Well, okay. So what do we mean by making sense? What we mean is this, right? What we mean is the meaning of this statement is this, that for any value of mu. Okay, as long as we have an IID sample like this, then if you form the expectation of the sample average, sample mean, then you get be able to be equal to mu. All right. So mu is unknown, agreed, but whatever value it is, 1, 10, pi, whatever, a million, this always holds. All right. So when I make this statement, I do not need to reference the actual value of mu. Whatever value of mu it is correct. Okay, this statement is correct. So that's why I can make these statements. Same thing here. Actually, here, right, the MSE, if you work it out, the mean square error will depend on theta, guaranteed. I'll be very surprised if it doesn't. Why? Because, you know, it directly depends on theta somehow, right? So, but on the other hand, of course, theta is unknown. So the MSE in the abstract is an unknown quantity, right? When we make this statement, we never claim that we know the MSE if we don't know theta. That's not what we claim. We just claim that this statement is correct, or it's just a concept rather. Okay, so we define like this. Okay, so theta is unknown. So yes, MSE will be by implication be unknown. If you give me a particular value of theta, I will tell you a particular value of MSE, right? So same thing here. So what do I mean by, you know, something that doesn't make sense when the population parameter is unknown? It will be in this context, all right? And I'll show you. Something that does not make sense is like this. Mu hat is going to be x bar over 2 plus mu over 2. This statement does not make sense. Do you see why? You see why this statement does not make sense? Yeah, mu is unknown. I mean, sure, right? But mu is also unknown here. So why is it that mu is unknown here that this makes sense, but mu is unknown here that it does not make sense? The reason, again, right, is because you have, right, exactly. Or what is the point of mu hat? What do you mean by mu hat? Right? What do we mean by mu hat? Well, mu hat is a estimator for mu, right? The whole point of mu hat is because mu is unknown, you use mu hat as a guess for it, right? So it's like if I ask you to guess what the number, right, in the box is, you say whatever that number is, divide by 2 plus 5. Does that even make sense? No, because I'm asking you what that number is. So here, right, the fact that you use mu here as an estimator for mu makes complete nonsense, right? So in this context, this, because mu hat, right, is an estimator for mu, you cannot use mu in it. Is that okay? But the statements right here, for example, right? So to make it even more pedantic, these are what we would say a probabilistic statement, probabilistic statement, probabilistic statement. And I guess roughly speaking, probabilistic statements don't really care whether mu is known or unknown, because it just tries to draw identity. This right here would be a statistical statement. because you would, try to say that something is an estimator of something else, etc. Right? So in a statistical statement, that you have to pay extra attention to see if something is known or unknown, constant or random, right? In the probabilistic statement, known or unknown, I think don't quite matter that much because, right, we just say it universally for any value, this is true. Is that okay? So, right, to recap, the message is very simple. Estimator cannot depend on what it's trying to estimate. That just cannot happen. Okay. All right. So going back to the unbiased thing, right? The unbiased thing. So for that matter, you'll see that the S prime square that we defined before, which is sum of xi minus x bar square divided by n, is biased for sigma square, right? Because we showed that expectation of S prime square is n minus 1 over n sigma square, right? Which is strictly less than sigma square. So a bit closer to home, right? Like another example would be, let's say x1 up to xn iid uniform 0, let's say beta, right? Let's try our beta hat to be the sample max. Okay. Now, the question is beta hat unbiased for beta? Now is a valid question, right? And how do we do this? Well, you see, to answer this question, we need to compute beta expectation of beta hat and compare it with beta. Okay. And you see why, right? To answer this question, we must know the sampling distribution of beta hat. Yes, because otherwise we cannot compute expectation of beta hat. Well, what is the sampling distribution of beta hat? Or, right, this is exactly the sampling distribution of the max, right? Remember, so that will be, right, the probability of everything less than this raised to n minus 1 raised to n times the density at that point, which in our case will translate to n x over b raised to n minus 1 times 1 over b, right? And of course, x between 0 and b. That translates to n x to the n minus 1 over b to the n. So expectation of the beta hat will be the integral with an x in front, which will be x to the n, right? So it'll be x to the n plus 1 which you see, right, is n over n plus 1 times b, which is strictly less than b. So beta hat here is unbiased, is biased, right? Okay, so that's another example. Any question so far? All right, so now, so biasness actually is not that big of a deal. Even though, right, I mean, you will hear unbiased estimator a lot of times. Biasness or unbiased, right? is not super important. Let me say this, okay? Now, when I make this kind of statement, I'm not saying it in any precise way because this is a qualitative statement, okay? It's like a judgment. But so don't quote me on this, meaning like, you know, it depends on what you do. But let me explain why it's not super important, okay? So first of all, it's not super important because of this. If you only focus on it alone. For example, let's say x1 up to xn, IID, right? Let's say mean mu and variance sigma square. Then x bar is unbiased for mu. But that's not the only one that's unbiased for mu in this sample. In fact, xi, any I, is unbiased for mu. Okay, what is xi here? By the way, right, I don't mean all the statistic here. There's no parenthesis, okay? This is just the ith value of the experiment, the ith trial, right? So for example, I have like a IID sample. I say I use the first value as the estimator for this population parameter. All right, I use the first value of my sample, not the smallest, the first value as an estimation for the population mean. Then that estimator is unbiased for mu, right? You see that? Why? Because what is expectation of xi for any I? Well, it's mu by definition, right? Because we say xi IID would mean mu and variance sigma square. So mean mu, right? Everyone here has mean mu. So you see, unbiasedness comes cheap. So what's the difference between these two types of parameters? Can anyone see? If x bar is unbiased for mu, xi, any I is also unbiased for mu, why do we use x bar as mu hat? Why don't we use any of these guys as mu hat? Exactly. Very good, Alice. Exactly, right? That's actually exactly why 10.3 needs to be discussed, right? It's not just bias, it's variance. And together, right, actually it's a mean square error. Exactly that the variance of x bar is sigma square over n, and variance of xi is sigma square. Exactly. So even though they're both unbiased estimators, right, mean square error of this guy is much smaller because the variance of this guy is much smaller, like Alice said. Exactly, right? So of course, right, the topics are discussed separately, but if you focus on one of them, it may not mean much. I mean, actually, right, so together, right? So unbiasedness, because of this, right? If you just focus on something being unbiased, that's you're being too fixated, maybe. Okay, so that's the first example. The second is like this, that even if you have a bias estimator, you can correct for biasness. Okay, so meaning you can modify an unbiased estimator, sorry, a bias estimator. I guess this is A, right? A bias estimator to an unbiased one. Okay, what's an example? You've seen example all this time actually. right? S prime square, right, is biased for sigma square, right? Expectation of S prime square, like we said, is n minus 1 over n at sigma square, right? So how do we correct for this? Well, observe that expectation of n over n minus 1 S prime square is sigma square, right? So whatever this guy is an estimator, and this estimator is unbiased for sigma square. So this right here, right, is the correction. Okay, so you see we correct S prime square into something, right, by multiplying with a constant that makes it unbiased. But of course, right, you know what this is. This is S squared. Okay, so your sample variance, right, the version that's division by n minus 1 is or can be viewed, right, as a bias correction from the S prime square. Okay, it's a bias correction. Okay. Any question? Another example, right, would be above. We have B hat, right, is biased for B, right? Because expectation of B hat is n over n plus 1B, right? So what is a correction of B hat? That would be unbiased for B. Exactly, right? Very simple. So you can call this B hat 2, right? Which is n plus 1 over n xn is unbiased for B. Okay. And so any question? So this, right, is another reason why I say unbiased is not that super important. What does that mean? You don't have to look for an unbiased estimator to begin with. You can just look for some estimator like S prime squared from your moment generating function, from your moment method, or from your MLE method. And from your MLE, from your method, right, you calculate what is mean is, right? And if it's not equal to the target, well, you correct for it. So you can construct an unbiased estimator, okay, out of your calculation. Question? All right. So let me say this, right? Caution, right? And again, this seems like obvious, but I'll explain. The correction, right, cannot involve the unknown parameter. For example, right, let's take this case. Suppose I take B hat 2 to be n over n plus 1 plus 1 over n plus 1b. Okay, that's my correction. Then is B hat 2 unbiased for B? Sorry. B hat 2 is B hat 1, sorry. Is B hat 1 plus 1 over n plus 1b. Okay. or just b hat, right? That b hat right here. Okay, I take this guy, I add this. Okay, so is b hat too unbiased for b? Well, the answer is right. The calculation will work out because you got n plus 1 over n plus 1. So you got b. But actually, right, you do not want to call b hat to estimator for b to begin with, because this term is just nonsense. Is that okay? Well, trust me, I have seen many things like this on the exam. So it's actually not that uncommon. All right. Students just use some unknown parameters in the estimation for some reason. So this is a place where it's a no-no. It just makes no sense. Any question? Okay. The last reason why bias is not super important is because maybe you have you may have a bias estimator, but you may have something that is asymptotically unbiased. Okay. So in other words, theta hat right, being an estimator is a function of, well, it depends on theta for sure, but it also depends on the sample size. Okay. So as you push the sample size to infinity, if the expectation is equal to theta, then theta hat is asymptotically unbiased for theta. Okay. For example, right, S prime square is asymptotically, I think someone mentioned this before, right? Unbiased for sigma square. Why? Because you see, this ratio goes to 1, right, as n goes to infinity. Beta hat as above also is asymptotically unbiased for beta, right? So the idea is there is some bias, but that you can live with it because that bias is small, right? That bias is small if you have a large sample size. So that's why, right? I mean, so the point is that, right, there are errors in life, right? You make errors one way or another, right? Bias is not the only place where you make error. Variance is the other place you will make error. And so you will hear this term all the time, right? The bias variance trade-off, right? Which is really a rule of thumb, I think. I'm not sure if there's a rigorous proof for it, but intuitively speaking, it's very easy to believe that if you reduce your bias, then you increase your variance. If you reduce your variance, then you increase your bias. But of course, right, the rate of increase and decrease are not the same for both for these guys. So they're usually, if you plot right the mean square error, right, there is a sweet spot where you got kind of the minimum mean square error, where you have a little bit of bias, but your variance is also small. So overall, right, I mean, people do live with biasness just to get the overall mean square error to be small. And so, right, that's the guy that we pay attention to. But anyway, right, I mean, to make it things easy, like the text, and of course, people do discuss biasness as a separate concept. But, I would argue that they live together as a pair, right, bias variance. You don't want to talk about one without the other. Any question? All right, so let's move on to 10.3. All right, so 10.3 is efficiency. And exactly it discusses, right, the other part of the concept, which is the variance. So the way the book describes it, right, is that basically efficiency, the way the book describes it, okay? So first of all, let me just say this. Efficiency, right off the bat, it just has to do with variance of theta hat. But the way the book describes it is like a relative concept because you want to compare efficiency. So, but that's just the way they do it. You don't have to think of it that way. You just can directly ask for the variance. Nothing really, nothing really. Suppose that, right? Suppose that, I don't know. Let's do this. Suppose somehow that the calculation come out to be this. I don't know how it come out that, but suppose that doesn't seem right because things should depend on it. But suppose like that. Then what do you say? Asymptotically, you have a 0.1 bias, right? Now it depends on the scale of life. Like, whatever you're looking at here, is 0.1 a big deal or a small deal, right? So, this is why statistics should not be discussed in an empty box. It should be discussed in a context, right? We name the concept here, we can talk about the concept here. But if you ask me if it's important or not, well, give me an experiment, right? Give me something. Then maybe I can try to tell you, yeah, it seems to make sense here, it doesn't, right? But so yeah, if it's not asymptotically unbiased, so what? Because remember, right, I said the goal overall is the mean square error. Like people deliberately live with a bias to reduce the variance, right? So that goes with also asymptotically unbiased, right? You could have something that's asymptotically biased, but its variance becomes small. I mean, that's probably much preferable. Okay, so right, so back to efficiency. Efficiency is it has to do with variance, but the way the book does it is a relative concept. So they would do this. Suppose you have two estimators, theta hat 1 and theta hat 2. They're both estimators for theta. Okay. Then I think it's pretty obvious to say that theta hat 1 is more efficient than theta hat 2 if variance of theta hat 1 is less than variance of theta hat 2. Right? I think that's very intuitive. And that's all I care to know. All right. I want to tell you that the book that defines the concept called relative efficiency of theta hat 1 with respect to theta hat 2. And I believe it's going to be variance of theta hat 2 divided by variance of theta hat 1. Okay. With the idea that if this is like, let's say, right, if this is like 1.5, then you can say that theta hat 1 is 1.5 times more efficient than theta hat 2, right? Because this means that variance of theta hat 1 is smaller, so it's 1.5 times more efficient than theta hat 2. Somehow the order of division just somehow, it's too much for me to remember, and I don't think I have use for this so much. So if you know this, that's good enough for me, right? If you know one is more efficient than the other, then of course we know what direction it should go. All right, so I don't care for the exact definition of relative efficiency. I won't ask you that, right? And frankly speaking, right, you see the core of the issue is what? How to compute the variance, right? Anyone can compute the ratio. Computing the variance, right, of the estimator is the point. So I won't bother so much with the exact definition here, right? But you understand what it means for efficiency, then that's it. Is that okay? All right, so let's look at the example, right? So example is where you may need well, one example is pretty easy maybe. That let's look at x1 up to xn IID, right? Normal mu sigma square. Now I need to specify to normal because I want, right, two different, I want to compute the variance. So I have two, right? I have two estimators for sigma square, right? S prime square and S square. We discussed that this guy is biased, right? And this guy is unbiased. Guess which one is more efficient? Or at least if you have to bet, right? Which one do you think is, which one do you bet, right, is more efficient? Yeah, right. I would bet S prime square is more efficient. Now, notice I say bet, right? I did not do any justification. To justify, you have to compute the variance of these two, which we'll do, right? But let me tell you why, right? You would expect this guy to be more efficient because this is biased, right? Remember the bias efficiency trade-off, right? So just rule of life, right? You win some, you lose some. You lose on the biasness, you should win back on the efficiency. If you don't, then that's too bad. That means like something quite wrong going on with the way you estimate stuff. So, right, because this one already lose out on the biasness, I would guess that it wins on the efficiency. Okay, that's more like it. Or if you want, if you pay attention to the structure of it, right? This one is division by n. This one is division by n minus one. Efficiency has to do with variance. The more you divide, right, the lower the variance. So you would expect this guy to win out. But let's do the rigorous calculation, right? Right, and that's where I need the normal assumption. So remember, right, what is the variance of S squared under the normal assumption? Well, if you don't remember, that's fine, right? But that's why we want to remember the structure of things. What's the fundamental result on S squared? N minus 1 S squared over sigma squared is a chi-square n minus 1, right? What's the variance of a chi-square n minus 1? Or chi-square n? Correct. So here, right? Oh, I'm so sorry, right? This is not equal to this for sure. What I want is variance of chi-square n minus 1, right? Well, of course, then you can factor this guy out as a square power. So variance of S squared is 2 sigma to the fourth over n minus 1, like that, right? Okay. So what about variance of S squared? Sorry, variance S prime, right? Actually, here you probably don't need to do the previous calculation. So I don't even need the normal assumption. I think I don't need it. But anyway, what's variance S prime squared? Well, what's the relation between S prime and S, right? S prime is S times n minus 1 divided by n, right? So that would be n minus 1 over n square, variance of S square. And I think that's enough. I think in a sense, the above calculation is redundant. This quantity is less than 1. So therefore, right, already I can say that variance of S prime square is less than variance of S square. So S prime square is more efficient. Is that okay? So actually, it'll be interesting, right? Then the last question is, in terms of mean square error, which one is higher and which one smaller? Right? So in other words, right, this guy is biased, but more efficient. This guy is unbiased, but less efficient. So mean square error, right, adds a bias square and the variance. Which one performs better overall? Okay, I'll let you figure that out. All right, so any question? Okay, so let's look at a less trivial example. Let's look at the uniform 0 to B case. And so how many estimators we have here? We have the MLE estimator, which is the max. We also have the method moment estimator, which is 2x bar. Okay, so these are two estimators. So we have shown, right, this is biased for B. Is this biased or unbiased for B? Is beta hat 2 biased or unbiased for B? Unbiased, right? Because expectation of beta hat 2 is expectation of 2x bar, which is 2 expectation of x bar. And expectation x bar here is what? Is the universal population mean, which is b over 2. Yep, so that's going to be b, right? So the moment estimator is unbiased. The MLE estimator is biased. Which one do you think is more efficient? Which one do you guess is more efficient? Well, again, right, rule of life, yes. This one has some biasness. So potentially, right, it sacrifice some biasness to gain on efficiency. So again, right, this is nothing rigorous. This is just like, so you can kind of make an educated guess. I would guess this to be more efficient. But of course, right, just because something is biased doesn't mean it's more efficient, right? You just can make a terrible estimator, right? You just see some really terrible estimator. So who knows, right? But all right. But so how do you compare the efficiency of these two rigorously? Well, clearly you have to do something like variance of this guy compare with variance of this guy. You see? And so this is why I don't care for the relative efficiency, because the bulk of the matter is to calculate this. Once you do this, anyone can form a ratio. So let's do the easy one first. What is this? What's the variance of beta hat 2? Okay, very good. I trust that you're right. So that's that. And variance of x bar, right, is going to be sigma square over n. What is sigma square in our case? Sigma square in our case is b minus a square over 12. Sorry, right? There's no a is 0. So, yep. So b square over 12. And that's exactly b square over 3n. So yeah, you missed the n, right? Yeah. Okay. Very good. Any question here? What about variance of beta hat 1? How would you calculate it? Well, there's nothing fancy here, okay? Like, you just have to look at where it comes from. It comes from all the statistics. So, all you know about all the stat is their densities. So you just have to work with the densities. What does that mean? Well, that means that you have to work with this, right? And we already calculate this to be n over n plus 1 b, right? The expectation. So you just square this term. So this term is taken care of. Ooh, did you do the calculation live right now? We'll check your. Oh no, that was your old answer. I thought you said beta to a 2/3. Sorry. So let's calculate this. Okay. So what is this? Well, that will be just expectation of the second moment, right? Of the max, which will be the integral from 0 to b x squared, right? The density which we calculated was n. Let me remember, right? X over b raised to the n minus 1 times 1 over b, right? Dx, right? Which will give me 1 over b to the n plus 1 over b to the n outside. I have the integral of, I can pull out the n, x to the n plus 1 dx, right? Which clearly is n over n plus 2 b squared. Right? So variance of beta hat 1 will be n over n plus 2 b squared minus n squared over n plus 1 squared b squared. Right? And you're meant to compare it with this. So some cleanup seems to be advisable. So that would be, right, n times n plus 1 square minus n squared times n plus 2 divided by n plus 1 square n plus 2 b squared. Okay, so what we have here, this is n cubed plus 2n squared plus n minus n cubed plus 2n squared, right? Which simplifies to only n. Okay. So what about the other one? The other one is b squared over 3n. which one do you think is smaller? Yeah, right. Because so when you do comparison, feel free to kind of assume that this is large to see what happens. If this is large, this is approximately 1 over n squared, right? And 1 over n squared clearly beats out over 1 over n. So this is definitely less. And if you do computer science, right, you see that the order is way different. One is the order 1 over n squared, one is the order 1 over n. Okay. So there. Any question here? All good? So by the way, right, this is one of the midterm problem that I gave before. You can see on the midterm that I shared. All right, this was one of it. Okay. So now we have 7 minutes left. So this will be the cap for midterm 1. Okay, everything up to this material. What I'll talk about next in the last 7 minutes or so will not be on midterm 1. Okay. And the topic of that is going to be the Cramér-Rao lower bound. So the Cramér-Rao lower bound is a very popular topic in stats, and it has to do with the overall question that we were discussing so far, which is we have theta hat as an estimator for theta. Well, actually, let's just say this, right? You have many estimators for theta. Okay, you have many estimator for theta. Let's say you have, theta hat I, okay, from 1 to whatever as estimators. You have a bunch of estimators. So ideally, what do you want? Ideally, you want to choose the theta hat I with the smallest MSE. Okay, you want to pick the estimator that minimizes the mean square error to your true parameter, and then you will use that in practice. And many applications, I think, try to aim at this guy, try to find this guy. Okay, I think machine learning tries to do this a lot. But anyway, in theory, though, right, which is what we're doing right here, minimizing the MSE is a challenging task because you have 2 terms. You have the bias and you have the variance. Okay, so minimizing these 2 terms together is rather requires some sophisticated math and a lot of calculations, even that. So maybe let's settle with an easier question. All right, let's settle with the easier question is, So, okay, right? Remember, MSE is variance plus bias square. Right, so if you want to look at everything and take the smallest MSE, that like I said, right? So meaning you have to minimize the sum, which may not be that easy. What you would settle down with is like this. You would settle to the subclass. Okay, we will specialize to a subclass of unbiased estimator. Okay. So if you look at the unbiased estimators, then clearly, right, MSE is just a variance. Okay. So then among these unbiased estimators, then the question is, right, among the class, right, of unbiased estimators or within the can we pick, right, one with minimum variance? All right. And here the question is actually pretty tricky. And when you think about it, the reason is this, right? That in the world of things, you think about, there are many unbiased estimators, right? Because you can do correction, that kind of thing. Suppose you come up with one estimator that has pretty good variance. Let's say, for example, right? Let's say x1 up to xn IID, mean mu, variance sigma square. Your x bar, right, is mu hat, is unbiased. For mu, its variance is sigma square over n. Seems pretty decent, but can we do better? In other words, maybe someone who's more experienced in statistics can come up with a mu hat 1 that's also unbiased for mu, but maybe the variance here will be n plus 1. I'm just throwing out example. But if that's the case, right, then whatever that mu hat 1 is better than yours because it has better efficiency, right? So the question is, okay, can we pick out, right? How do we know that we have achieved the best possible? And if so, right, like what is that limit? What is that bound? So Khmer round gives you exactly an idea of your limit, all right? In the sense that Khmer round lower bound says that if theta hat is unbiased for theta, then the variance of theta hat is lower bounded by this quantity. Okay, this quantity. So this right here is a quantity that maybe you have seen before. This is the population density or population distribution function. It also is called the Fisher information, all right, and it's connected with the likelihood function. But anyway, right, it tells you that this is the absolute bound that no parameter has variance can be lower. So if you have a parameter, sorry, no estimator. So if you have an estimator that reaches this, then that's the best you can do, and you know that you have got it. Okay, so we will continue then. We reach time, right, with this topic on next Tuesday. All right. Okay, thank you for joining, guys. If you have questions, I'll answer them. If not, see you on next Tuesday. Thank you. You too.
Oh, have you ever mentioned about what kind of things I can put on the note for the midterm?
Unrestricted, as long as the font size and the spacing is reasonable. Yeah.
Okay, thank you.
Professor?
Yeah.
I had a question about something